And they can start. Okay, today we have Enoch Leung from Max Planck Library to talk about resolving continuous symmetries in holography. Thank you for coming. Please take it.
Yeah, it's my pleasure to give the online seminar here. Right, so today I'd like to share some results from a couple of papers that I posted with my collaborators, Ibu Ba, Federico Bonetti, and Mufaro Chitoto. One came out the end of last year and the other came out a few months ago. Okay, so without further ado, let me start trying to motivate why we want to talk about like continuous symmetries in holography. So as with many of the talks that are similar here, we want to talk about how generalized symmetries appear in modern study of QFTs. Especially when we talk about global symmetries, they're very useful in characterizing your QFTs and how to study various data in it. And the notion of global symmetries in the past decade or so has been generalized to various notions, including higher form symmetries, higher group, or more recently to non-invertible, or somebody would call it the categorical symmetries. And this generalization is very well understood nowadays in terms of the study of topological operators or defects. And by the way, in this talk, I'll try and introduce
Can I interrupt and ask a question?
yes.
So higher group, is that in the categorical sense, or what does higher group mean?
There are various ways to understand higher groups. One way to understand it is through traditional math like higher group, and you can also okay, this way it tells you how you can have different symmetries, and the gauge transformations are not just transforming under their own group, but they also mix with each other. So that's one way to understand higher group. Also, an alternative way to understand it categorically is to have like some higher categories, let's say two category, where you
Right.
have different
So
layers.
is there a notion of higher groups which does not refer to category theory?
Um, I guess for this slide, I try to distinguish the high group, the standard high group that's used like if you use
Okay, I'm not familiar with what standard higher group is. So that's probably my question. What is standard higher group?
I guess one easy way to understand it is for example, you have two symmetries like G1 and G2. Maybe G1 is, let's say, a zero form symmetry, and G1 is, I don't know, like a one form symmetry. And then if they are honestly group-like symmetries, then the gauge fields for G1 will transform in a G1 way. And if symmetries, the gauge fields for G2 will transform according to how it transforms in a G2 fashion. But then there are also cases where when you transform one of the gauge fields, it's not totally invariant, and you need to subject it with additional transformation from G2, for example, one way or the other. So this is how different symmetries with different form degrees can mix with each other, and this is what I mean by high group here.
I must say I still really don't get what the difference is. What the higher group is. So you say P1 and P2, and then of course we can talk about I guess the product group of P1 and P2. But what is higher group?
I guess as far as the slide is concerned, higher group is just a fancy way of saying that it's not a direct group, and you have two groups with different form degrees and one acts on the other.
Oh, okay. So you mean like a semi-direct product, or?
That's one of the examples that you can think about. But I'll not touch on higher groups in this talk for the bulk of the talk, so it's not really crucial here.
Okay, go on.
Yeah. Right. So yeah, in a broader sense, these are all captured by some notion of categories or higher categories, if you will. Good. So let me just quickly review how this development happened. So back in QFT 101, if we have a Lagrangian for QFT, And we say that there is symmetry if this Lagrange is invariant under the action from, let's say, a Lie group, G. And so because of Noether, you find that there exists some d-1 form current, which I call star J here, that is responsible for generating these G transformations on the theory. And moreover, this current is conserved in the sense that d of star J is 0. And so because of this conservation equation, you can cook up operators in your theory, which I call the symmetry generators. That's essentially the exponential of this star J integrated on some codimensional manifold. And the property of this symmetry generator is that it's topological in the sense that if you deform the support of your operator by a little bit, more precisely by the boundary of some higher dimensional manifold, then because of the current conservation equation, then this operator is the same as itself.
Right. And this notion of global symmetry, that's just zero form symmetry, right?
Yeah.
Yes. As far as the Noether theorem is concerned, yes. Good. So if you cook up this operator, so the symmetry generator, it generates G actions on your theory, and it measures the charge of local operators. Your local operators mean point-like operators in your theory. So just the standard way of thinking about symmetries. Now, because of this seminal paper by Gaiotto, Kapustin, and Cyber and Willett, about 10 years or so ago, you can actually understand this from a opposite viewpoint, which is that given a QFT, if you find that there exists some set of topological operators, that means that there is some quantity which is conserved in your theory, and which means that it implies that there exists a global symmetry of the QFT. And so this viewpoint is very powerful because you can easily generalize it to like this notion of high form symmetry or P form symmetry in general. Where if you have a P form symmetry, then you have codimension P plus 1 topological operators. In the previous case, the standard symmetry is basically a zero form symmetry where you have codimension 1 topological operators. And for general P form symmetry, it acts on dimension P operators. So for example, if you are in 3D, and if you have a one form symmetry, then the symmetry generators are lines. They are one-dimensional objects. And because of the dimension, the operators that the lines act on are also lines. So basically you have lines linking with lines in 3D, which is the usual statement. But this generalizes to any other dimensions. And one defining feature of these P-form symmetry operators is that the fusion rule is group-like. So if you fuse an operator corresponding to some group element G and the other corresponding to a group element H, the result should be the operator that's labeled by the composition of the group elements in a group. So this really shows that this is a group-like action. And one advantage of this P-form symmetry is that in the Noether procedure, everything is like continuous. And so a notion of current is well defined. But if you think about symmetries in terms of this picture of topological operators, then you don't need to restrict yourself to the realm of continuous groups. You can even probe like discrete groups, which doesn't really need a current. And all of this picture still applies. So another advance from P-form symmetry is what's called non-invertible symmetry nowadays. Non-invertible means that operators do not necessarily emit inverses. So in a previous group-like symmetries, because symmetries live in a group, then you'd always have inverses in a group. But for non-invertible symmetries, your operators do not necessarily need to emit inverse as long as they're still topological. And these things exist in many examples. So one example is the Kramers-Wonnet duality defects in the 2D Ising model at the critical temperature. And so a modern understanding of these non-invertible symmetries is that they're mathematically described by fusion categories. Or if you're in a higher space-time dimension than 2, then you're supposed to be described by high fusion categories. Good. So we've seen a lot of different notions, generalizations of the notion of symmetry, and one framework to understand this in a very systematic way is called the SymTFT, Symmetry Topological Field Theory. That's proposed by the references I listed here. So basically, the SymTFT is a very convenient mathematical tool that kind of helps you dissect or isolate the symmetry data from the very complicated dynamics in a general QFT. So what happens is that if you have a single QFT in D dimensions, you can basically blow it up, resolve it into a bulk, which is in one higher dimension, this D plus one dimensional TQFT. And it's sandwiched by two different boundaries. One is a gap boundary and the other is a gapless boundary. And this kind of mathematical structure has proven very useful for people to understand how symmetries interplay with each other and to ignore the dynamics, which doesn't really dictate the selection rules and whatsoever in the QFT. And actually, this notion of SymTFT is more than just a mathematical trick. It has like very concrete physical motivation, or like there is a realm where this actually appears naturally, which is the ADS-CFT correspondence, or holography in general. And here the idea of this ADS-CFT is basically that if you have a QFT on a conformal boundary of some ADS geometry, and this QFT is dual to some string or M3 background in the bulk. And as far as symmetry is concerned, what ADS-CFT tells us is that if you have a global symmetry on a boundary QFT, then it's dual to bulk gauge fields in the string theory background. And so we would like to see how to utilize ADS-CFT correspondence to help us study symmetries in QFTs that we like. Now, this idea of studying symmetries and through the ADS-CFT has been very useful, and in particular in this modern generalized symmetry business. Many people have been trying to model the holographic duals of symmetry generators and the charge operators in terms of like D-brane degrees of freedom in the string theory bulk. And the common feature of these studies is that if you imagine you have this ADS bulk and you have a QFT lying on the boundary, what you find is that the symmetry generators are objects that totally stick on the boundary. They're localized on the boundary. Whereas charge operators are things that extend into the bulk and end on the boundary. So here I illustrate the case for zero-form symmetries where you have a codimension 1 blue line that's linking a point on the boundary. So here you can literally think of this as a Wilson line with an endpoint on the boundary. So this quest to study symmetries in ADS-CFT and how to study it in a modern lens works tremendously well for finite symmetries, including both invertible and non-invertible symmetries. And we find that using what we know about string theory and branes in the bulk actually successfully captures a lot of field theory results. So this is like a very promising direction to study. However, this only applies for finite symmetries so far. And we would like to see how to extend this to the notion of continuous symmetries. And one technical challenge of this is that if you know how the SymTFT is constructed, the inherent categorical language of the SymTFT actually does not really apply when a symmetry is not finite or discrete.
Another question, when people are talking about continuous symmetry, then they usually take it as opposed to discrete symmetry. But you talk about finite symmetry. So do you want to say something about discrete groups or discrete cases?
Yeah, so discrete groups are finite, but
Yes. No, not necessarily.
So there are some like maybe slightly more exotic examples. So one example is the group of Q mod Z, so rational numbers modeled by integers. So we have infinite number of rational numbers. So it's not a finite. So it's not a finite group, it's a discrete group. So there's some technical subtleties in whether we want to talk about finite groups or discrete groups. But it's not too important for today's talk. We'll just go from finite to continuous. We will not try to distinguish between finite and discrete groups in this talk today.
But why can't we? I mean, for instance, we usually say a lattice. Then we would say that's a discrete symmetry.
Yeah, I mean, but at least most of the discrete ones we are interested in are like physically finite. So
Yeah, well, not necessarily. I mean, that could be an infinite symmetry.
what physical system would that be?
Yeah, but anyway, but just mathematically, you could have that.
Yeah, there are examples where you can have discrete but not finite groups.
Yeah.
And
So,
people.
okay, so we are excluding that for now.
Sorry, can you repeat that again?
So we are excluding that case. So discrete non-finite, we're excluding that for simplicity.
Yeah. If you like, you can just replace all the finite in this talk with discrete, and that will not cause any problem.
Okay, so it doesn't really have to be finite.
It doesn't have to. Here, I'm trying to be technically correct, so that people who actually invent the CMTFT won't go after me, but that's fine. Yeah. So like the contrast I want to make today is from like discrete symmetries to finite symmetries to continuous symmetries, which really is a drastic change in the topology of the group. Cool. So let me continue. So in the past 1 or 2 years, there have been several proposals to try to extend the SymTFT prescription to continuous symmetries, which are all very wonderful and excellent. But to the best of my knowledge, a very precise mathematical description is still lacking. So there is not any rigorous formulation of the SymTFT for continuous symmetries. But today I'm not quite heading in that direction. There's another more physically motivated reason why we would like to consider to study continuous symmetries and actually analyze the subtleties. And the issue is that if you have continuous symmetries in your QFT, very often you have to regularize things for things to be well behaved. And this is actually not even avoidable if you consider turning on gravity in your QFT. So if you're a person that likes to think about quantum gravity and you want to regard a QFT as a low energy limit of some quantum gravity theory, then this is something that you should keep in mind. So we would like to see how regularization pops up and how to actually see that manifest in the context of holography and what that implies for what the symmetry operators look like in the string theory bulk. So our approach is to make use of string theory and holography to see whether it can give us hints on how to tackle these problems to like render the mathematical description of symmetry operators well defined. So that's how we would like to think about the problem that we're studying today. Any questions so far? If not, let me proceed. So let me try to set up the playground for us today. So we would like to study zero forms continuous symmetries in a d-dimensional QFT. And for simplicity, we'll restrict G to be a compact and connected Lie group, which may or may not be abelian. And we want to particularly focus on non-abelian things because that's where the structure manifests most obviously. So in ADS CFT, this QFT will be dual to some d plus 1 dimensional ADS space times some internal space, which I'll call X. And this solution is embedded in type 2B or in M theory, whatever you like. And so you can just derive, using your favorite method, the low energy effective theory of this ADS times X solution. In particular, it involves the following terms: engaged supergravity, which is the standard Yang-Mills term. And depending on the dimension, there may also be some Chern-Simons term involving some couplings in the super theory. And so here, I'd like to unpack the notation a bit here. So when I have these FIs or AIs, what I really mean is that I'm using it as collective notation. So in string theory, there are typically two kinds of geometric origins where these low energy effective gauge fields can appear. One of these classes is that it can arise from the isometries of the internal space X. For example, if you have a sphere in your internal space, then you can have you have an SO whatever isometry, and then this will manifest as some SO whatever gauge fields downstairs. And so here you have one class of symmetries of gauge fields arising from isometries of the internal space. The other kind of gauge fields arise from the presence of homological cycles in your internal space X. So for example, again, if your space has some cycles, then by reducing your supergravity flux or potential, let's say C4 or C3 in 2B or M3 over some 3 cycle or 2 cycle, and 4 minus 3 gives you 1 and 3 minus 2 gives you 1, then you get a one-form gauge field downstairs. So there's another mechanism in which gauge fields can arise downstairs in your low energy effective theory. And today we'll cover both kind of geometric origins of these gauge fields. Right, so if you're a string theorist and you're interested in this top-down description, yes, this is how things arise, but as a low energy person, you can just take this as the effective theory that you start with and try to see how you can cook up the symmetry operators. And this is the approach that we're gonna take in the next few slides. So as I described in the picture that I showed previously, there are two key players in the game of symmetries, namely the charge operators and the defects which generate the symmetry. So we'll first focus on the charge operators themselves. And so as you see in the picture before, these charge operators are basically Wilson lines that ends on a boundary as a local operator. And these things arise in holography as these bulk Wilson lines of gauge fields of the low energy supergravity theory. And so one way to construct them is, of course, to just use the familiar expression of the trace of the path ordered exponential of the gauge field. So this is good and very elegant. But then for our purpose, we would like to use a different model, which is to reformulate this formal expression as a 1D quantum mechanical model. And the action of this quantum mechanical model is as follows. So it's given by this inner product of Q and this term here. So let me unpack this notation a bit again. So here Q is a constant parameter that's valued in the dual Lie algebra corresponding to the gauge group that we're interested in. And chi here is a dynamical scalar field that's localized along this 1D world line M1. And it's a scalar field valued in a group such that this whole combination chi inverse dA chi is a combination valued in the algebra. And so that it makes sense to talk about inner products, where this inner product is taking in a pair of data from the dual Lie algebra and the algebra and spits out a number. So this is the 1D quantum mechanical model that we want to invoke for the Wilson line. And I'll show for you very soon how this thing is equivalent to the usual familiar expression of the trace of the path ordered holonomy. Now, if you try to analyze this quantum mechanical model and you want to quantize it, because we're working with, we want to quantize it just like how we quantize Chern-Simons theory. And so this gives rise to quantization conditions where Q, this constant parameter here, is actually what's formally known as the analytically integral weights. And I'll not explain the details of this, but then there's this famous result of the theorem of the highest weight in representation theory, which tells us that this parameter Q is actually in one-to-one correspondence with a rep R that labels the Wilson line in the previous formal expression here. In other words, if you want to have a Wilson line in whatever favorite representation that you like, basically have to cook up the appropriate parameters Q that labels the representation here. So we've turned the problem of determining this abstract representation into an actual problem of measuring these numbers Q in holography. And the advantage of doing so is that these numbers Q actually arises geometrically from the internal space. And there's a very nice geometric origin of how these things arise. And we can see very geometrically how to measure these numbers Q. As I'll explain later. So let me try to pause for a moment and see whether there are questions. Okay.
So I guess this action. So the point is to reproduce this Wilson line. You have to write down some path integral over so a group value path integral over that.
Yep. So we basically want to have like a much more down to earth action for us to actually write down explicitly and know how to manipulate algebraically. Right. And the purpose of that is just to replace this very formal expression, which is kind of not as practically useful for a purpose.
Right.
So that's what I'm trying to do here. Exactly.
Yeah, I think this construction is quite old. I mean, that yes. I remember talking with people about that around in the early millennium. I mean, 25 years ago at least. But yeah, so this I think is standard construction.
Yes, this is known for quite a while. And we want to like just make use of this prescription to help us see how things appear, basically. I totally agree, yes. Okay, so let me try to provide a few examples to see how this actually works in practice. So the first example that I want to consider is that I choose the gauge group G to be SO(n+1). And here I want to limit to limit n such as SO3 or above. In the case of SO2 would be considered separately later. And once you pick G to be SO(n+1), you can just write down manifestly that the Wilson line action is given by this formula here, where QAB is a block diagonal matrix given by this form. And so the reason why you have this kind of G equals SO(n+1) structure arises because you have some n sphere in your internal space. And so, for example, you can parameterize this internal space by the usual expression where you add up the squares to give you 1. And my claim previously is that the parameter Q actually arises geometrically. So let's see how to see that explicitly. So suppose I wrap some brane, indeed n-1 dimensional brane, on the following manifold. So I wrap it on some external support. That's a line that's supposed to represent the Wilson line, and some internal n-2 sphere. So this is a codimension 2 sphere inside the n sphere in my internal space. And one way to do this is to set maybe, let's say, 2 of the components y here to be 0. And that would define for you the equation for codimension 2 sphere inside Sn. Now, we're proposing or conjecturing that the action for this brane contains a coupling, whereas the pullback of a supergravity flux Gn, degree n flux. And because we're working with gauge supergravity, then this Gn flux actually contains terms that include these Fs, the gauge field F, for the SO(n+1) gauge group. And here, it is very important that this is a pullback of the supergravity flux onto the world volume of the brane. And the effects of this pullback is, crucially, it induces some dependence of the action on some real-world word volume scalars, chi. And you can do this explicitly, and it's done in our paper. And one physical interpretation of these chi is that it describes the shape of the brane that's inside your Sn. It describes how to parameterize this Sn-2. And moreover, in this action up here for the Wilson line, you can perform a gauge transformation on these chi's. More specifically, an SO(n+1) transformation on the chi's. And leave this whole action invariant. In other words, this chi actually describes how to rotate this codimension 2 sphere within the Sn factor. And so this kind of tells you how you can embed your Wilson line within this internal sphere and how this is actually, you can fluctuate it as long as preserving some maximal codimension 2 sphere. And so once you have this coupling, and you can just do some algebra, and you can show that this actually reduces downstairs to this effective action here. And here you can see that this action is very similar to the formal expression here, as long as we identify QAB in the formal expression with this combination. And here this N is just the N in the usual ADS CFT where it labels some integer flux number. And W here actually tells you how many times the brane wraps around this codimension 2 sphere. And this NAB is just a set of numbers that encodes how you define this maximal codimension 2 sphere. So now you can see how these Lie algebra parameters QAB has a very nice geometric interpretation in terms of how you're defining support of your brane inside the internal space. And actually this recovers one of the old results in the string theory literature, namely that if you consider type 2b on ADS5 times S5, these branes actually correspond to D3 branes that manifest as giant gravitons in the theory. So there's one example, and it actually applies more generally to as long as you have any sphere factors and you have some SOM plus 1 gauge fields. This prescription still applies. So let me top out a few other examples for completeness. An example is U1, or in other words, SO2. Here U1 can either arise from a single circle or one circle in the internal space, or it can also arise from some homological cycle in your internal space. So here, because everything is abelian, then the word volume scalar chi actually decouples from the theory. And so you recover the standard expression where you have some charge, integer charge Q times the holonomy of A. That's the familiar Wilson line expression for U1. And again, here Q is proportional to the wrapping number of the brane along the cycle. Now you can also consider other more non-abelian examples. For example, you can consider spin n plus 1. So since spin is the double cover of SO, so everything that I mentioned in the XO example actually applies. Except that now you also have the freedom to choose these Q charges to be half integral. And the half integral ones actually correspond to nothing but the spin representations. So it's kind of like one stone with two birds. You have pretty much the same prescription, but you can apply it to spin representations or the more ordinary ones. Another example is SUN, or SUN plus 1. So you can have SUN plus 1 gauge fields arise in supergravity as long as you have some CPN factors in your internal space. And we'll see examples of that later. And so here, recall that in the previous SO examples, the prescription is to wrap the brane on some codimension 2 sphere. And here there's a very similar example, similar phenomenon happening. What we want to wrap is that we want to wrap a complex codimension 1 CP inside the CPN. And so the difference between this example here and the previous SO example is that instead of having real scalars, what you get instead is complex scalars. And these complex scalars actually parameterize the theory. And it parameterizes how you are encoding this CPN minus 1. And the nice thing about all these different prescriptions is that they are compatible with exceptional isomorphisms. So for example, one of them is that you have SO3, which is isomorphic to SU2 mod C2. So in the SO3 description, we want to wrap a codimension 2 sphere inside a 2 sphere, meaning that it's a zero sphere. And a zero sphere is just a pair of points. Whereas in the SU2 prescription above, we want to wrap a complex codimension 1 CP. So a TP0 within CPU1. And so this gives you 1 point, a single point. And a single point is just, roughly speaking, half of a pair of points. And so you can also check this against other possible exceptional isomorphisms, and we can find that these prescriptions are all compatible with each other. So I hope that this illustrates how, given a general Lie group, you can find some prescription how your brane wraps some internal factor, and this will give you the appropriate Wilson line prescription with the appropriate Q parameters. And very often these Q parameters are proportional to how you wind these codimension whatever things inside your internal space, and it also encodes how these things fluctuate within the internal space. Okay, so having constructed all the Wilson lines, let us turn our focus on how the symmetry defects are constructed, because you need the symmetry defects to measure the charges. Okay, so recall again that we have this low energy effective action in supergravity. So it's straightforward to read off the Gauss law constraint from this action here, which takes this form here. So here, the capital D is a covariant derivative that we all like. And depending on dimension again, there may be some transcendence contribution. And as far as the bulk is concerned, this Gauss law constraint actually generates gauge transformations for the bulk gauge fields. But what we're interested in is that we were interested in the global symmetry in the boundary QFT. So we want to push ourselves all the way to the boundary and impose Dirichlet boundary condition on the gauge field. In other words, the general Gauss law constraint reduces to a standard current conservation equation. Little d star j is equal to 0. And what this does for you is that it generates, or it realizes, a global symmetry on the boundary. So again, since Noether tells us that, okay, as long as you have a charge conservation equation, a current conservation equation, then you hook up a symmetry generator. This in this form here. Now I'll say this is a naive construction. And why is that a naive construction? This is because that in QFT, what we want to do is that, because everything is quantum mechanical. So instead of just the current conservation equation, you really should look at Ward identities, which kind of takes this form. And so imagine you have this symmetry defect that I constructed earlier, which is exponential of star j, basically. You want to insert this kind of things in your correlators when you compute whatever observables. And you need to formally expand this exponential into powers of star j. And once you have powers of this, you see that if you basically have to repeatedly apply Ward identity in your correlator. And you get like multiple powers of delta functions. And this kind of raises a red flag, like this is not quite a well-behaved thing. Once you have multiple powers of delta functions. And so one way to do this is that you want to regulate this behavior and produce a well-defined operator by thickening up the defects. So basically, instead of having a step function that kind of changes things abruptly across where you insert your defects, you want to thicken it up and give it a smooth profile, such that in the limit where you shrink the width of this domain wall to 0, you recover the step function. So a mathematical way to write this down is the following. You can, instead of having just star j, you insert some bump function that smoothly generates this gauge transformation, plus some higher order corrections. So, and you can see from examples shown in this paper that once you define this kind of regularized defect, then you do recover the desired behavior for your correlators. So this is how you should define the defects as long as continuous symmetries are concerned. So you can view this more generally, which is that in this expression here, if you look at this combination theta f prime, by construction, this is flat because it's already a derivative of someone else. So you can actually replace this with a more complex expression that is some flat A1 times star J in your regulated defects. And so the way to see, one way to see why we want to write it in this way is that we want to see how we actually measure charges in your QFT. So imagine you have some local operator here, and you want to measure it by pulling this defects across it. And since this is a thickened up defect, you can actually see explicitly that once you pull it across the defect, in the intermediate stage, you actually drag out a Wilson line of this little a here. And at the end of the charge measurement process, meaning that you pull the defects all the way to the other side of the local operator, you can integrate up this Wilson line and get a phase. And so in the limit where you take the width to be 0, then you recover the standard phase that you measure as a charge of the local operator under the symmetry. So this is how once you regulate and thicken up the defects in your QFT, there is some smooth gradual charge measurement process that happens. And the main goal of this project is to see how to replicate this kind of gradual charge measurement process in holography. And so again, our conjecture is that there's some brane, which I call a hanging brane, that has this following effective action.
Question, sorry. In the previous slide, the Wilson line is associated with the topological object, is it? I thought usually the phase is associated with the local operator, not the topological operator.
So here, this Wilson line is a Wilson line of its little a. So here, so this little a, you can think of this as a connection constructed out of this bump function here. So, so intrinsically, it has nothing to do with the symmetry group itself or the bulk gauge fields itself. It's just a local thing that's living on top of this defect.
But wouldn't the defect be unaffected? I thought only the scalar field gains the phase and the defect still remains unaffected. But here, the defect has a Wilson line in the scalar field. I'm just going by the image, but
right. Yeah.
So just like I thought the scalar field was the one that gains the phase, not the topological operator itself.
The scalar field remains as it is. It's still a scalar field here, phi. And usually when you do QFT, right, the naive way that you do this is that you see that the phase transform with a single phase, exponential of some number. And here, basically, what we've done here is to resolve this phase into a Wilson line, give it a geometric interpretation.
Yeah, but I was thinking more along the QFT lines. For example, if you have a zero-dimensional form, you take like zero-dimensional symmetry, you take this across, the scalar field gets a phase. For Wilson lines, if you have a 4-dimension one object, you take it across, the Wilson line gets a linking number or something like that. But here it seems like the topological object is the one that is being affected, like from the picture.
Yes, that's our proposal. And these two, I don't think these two things are in contradiction with each other.
I see. Okay.
And you can actually see this explicitly if you take this kind of operator where you have A1 wedged with J, you see that actually drag out a phase like this.
Okay.
Yeah. And yeah, this in some sense, this is instead of doing just a blinking, which is instantaneous, in some sense, just doing this gradually.
Okay. Thank you.
And in the end, if you actually integrate this whole thing up, which does give you a single complex phase, then this will give you exactly the phase or the charge that you measure normally. Yeah. Thanks for the question.
Yeah, thank you. So,
any other questions so far? Okay, so let's resume. So we're proposing that in holography you have this kind of objects that emits this kind of coupling here. So here gamma 1 here is I'll show a picture of what this looks like in a second. Here, gamma 1 is an arc whose endpoints actually lie on the conformal boundary, but it stretches deep into the bulk. And here, A1 is a flat word volume U1 gauge field with some dirichlet boundary condition. And this A1 is supposed to mimic this A1 here in the field-theoretic construction. And we do see that in string theory or M theory, there are a lot of branes with some localized degrees of freedom. So that's something that's naturally found. And here, Ni actually encodes how you wrap some internal submanifolds. And so you see that this kind of objects with this kind of coupling can be identified as a symmetry generator, as long as you identify theta I and the naive construction here, theta I, with this data here, alpha and times Ni, where alpha is the holonomy of this word volume gauge field along this gamma 1 arc. And Ni encodes the wrapping data. And so if you think of theta I, which is a Lie algebra element, it's a vector in some vector space. So alpha actually labels the magnitude of this vector in the vector space, whereas Ni actually encodes the direction in which you point in this Lie algebra. So this again gives you a geometric interpretation of how these AIs and NIs encode this Lie algebra element. And so if you have this kind of operator, what this does for you is that it labels a group element that's the exponential of this theta in the Lie algebra, which gives you a group element. So this recovers the statement that we want to construct symmetry defects or symmetry operators that are labeled by the group elements. And so for each group element, you can always find some Lie algebra element that gives you the correct group element under the exponential map. So this gives you a full, complete set of operators as these hanging branes in a bulk. So the visual picture that I would like you to have in mind is that the hanging branes that we constructed takes this kind of form. So it's some codimension 1 operator on a boundary, but then it stretches into the bulk through an arc. And so this effectively thickens up an infinite thin codimension 1 object into a smeared objects. And so in string theory terms, you can actually interpret this kind of hanging configuration as some brane and antibrane that recombines in the bulk. It's a brane and antibrane because they have opposite orientations. And one may ask whether this kind of object will like dynamically collapse into itself because the brane and antibrane tends to annihilate each other. But then we can see that because of the special properties of the ADS geometry, this kind of brane that hangs or anchors on a boundary actually is dynamically stable. So they won't naturally collapse into something on the boundary. But now, once you have this kind of configuration in holography, it makes sense to talk about this partial charge measurement that we saw in this cartoon picture in QFT here. What happens actually in string theory or in holography is that once you put the Wilson lines, which we constructed earlier, through this kind of hanging brane, it drags out some trace on this arc here that's labeled by this red line. And so it also makes sense, in particular, to drag this gradually without, to basically drag this in a smooth manner and top out this gradual charge measurement process. And this is what's commonly known as a Hanani-Witten transition in string theory terms. So you can also ask whether in holography you can make sense of a zero width limit where you shrink this hanging arc back all the way back into an infinite thin slice. And the answer is actually yes and no. So one way to see this limit happening is that you can do tachyon condensation. And once you do this tachyon condensation of this pair of brane and antibrane, what you find is from the following gentleman, is that you can have a non-BPS brane that's localized along the boundary. But this is good as far as you don't really consider dynamic gravity on the boundary. Of course, in standard ADS-CFT, you do not have gravity on the boundary, but if you want to think about it in a broader term where you want to think of boundary QFT as just some low energy limit of quantum gravity, and if you want to turn on dynamic gravity at the boundary, this is actually not possible. So you cannot really collapse this configuration all the way back down. In other words, when you have gravity turned on, these symmetry generators must be domain walls that have finite width and tension.
Can I ask a question?
Yes.
So when constructing non-invertible symmetries, they do this higher gauge method. You have boundary like with one particular orientation, and then you have like another orientation reverse boundary, and then you collapse that and say that is now your non-invertible symmetry to take it to zero width. So is that a similar picture here?
It's a very similar picture that I do admit, except that the way it acts on operators is slightly different.
I see.
Yeah, and that you can't quite see this from this kind of cartoon. You really have to work out the algebra of how the operator acts on operators. But I do agree that the mental picture that you have in mind is very similar. In particular, you see how like this drags out a line that's kind of reminiscent of how non-invertible symmetries act on operators. But it's not exactly that, especially that you can take a limit where you shrink this all the way back down. It gives you a single phase instead of having a line that actually is like left out there.
I see. Okay,
Yeah.
thank you.
But yeah, thanks for the comment. It's a very nice observation, and we find it very intriguing as well. Maybe there's something deeper in that, but
No, because like in this is the exact picture you take. Like when you say, okay, you want to higher case that you have one boundary and then like you have two different boundaries. So internally you have one of the non-anomalous symmetry group to be caged, and then when you shrink the gauge area, the gauged bulk part to like completely collapse on each other, you say that now you have a non-invertible symmetry. But here you are saying that if gravity is turned on, you cannot do the collapse like to a completely a single line, right?
yes.
Yeah.
And one reason to kind of understand that is that when you have dynamic gravity turned on, like things are no longer fully topological.
Yeah.
You can freely like take any like limit to like a zero width or whatever. Like things are fluctuating all the way. So that's one way to understand why you can't really take this limit if you consider full flat gravity.
Okay. Thank you.
Okay, so right. So let me also comment on how these hanging geometries fuse with each other. Like our motivation is to construct symmetry defects that generate the G symmetry. And so if this is the claim, then these defects should be able to fuse under composition. Right. So the way to see this happening in this kind of hanging configurations is to consider, right? So in the most general case, you apply BCH formula to get this kind of non-trivial structure that's reminiscent of how you fuse operators in quantum mechanics, for example. There's a very nice interpretation if you consider a special case where these combinators are zero. In this case, you can consider the kind of picture here on the left. So you consider a few hanging branes stacking, not stacking, you align a few hanging branes in a junction. You want to try to fuse one after the other. So there are two ways to fuse this. You can fuse the two on the right or the two on the left first. So what happens is that it kind of reshuffles these lines here. So I label these arcs, the branes or anti-branes, with different colors, just to showcase how you have to take care of the orientations. So you basically fuse it in a way such that the arrows align with each other in the same way. And so you can continue this process kind of multiple times. And you see that you'll be able to fuse into this kind of configuration, which can further fuse into this kind of configuration. So what happens is you can align a few branes next to each other and you can fuse them together such that it gives a stack of branes whose effective group element that you're labeling is basically summing up these vectors in your Lie algebra. So this gives a nice and geometric way to see how we can make sense of the fusion of these hanging branes. And of course, if things don't really commute nicely, then there's actually a highly non-trivial rearrangement of the internal geometries that you can't quite see downstairs in the supergravity theory. You'll only be able to see that when you actually write down the full expression in the UV and see how things changes. So now I'd like to give a few examples of explicit top-down string theory constructions to see how these things arise naturally. So since we're doing ADS-CFT, the canonical example that we all study in the first place is ADS 5 times S5 in type 2B. And so here, the symmetry that we're concerned about is the SO6 isometry from the S5 vector in the internal space. And this isometry and this SO6 isometry is dual to the R symmetry in 4D and includes 4 Yang-Mills theory, with the following effective action in the bulk. So one thing I want you to pay attention to is that this effective coupling in the Yang-Mills term actually has 2 contributions. There's one contribution from the flux sector, the RR sector in 2B gravity, supergravity. And there's also another contribution which is coming from the Einstein-Hilbert space. The Einstein-Hilbert term, sorry, the Einstein-Hilbert term. And the way to see where this Einstein-Hilbert term arises is because you've gauged the metric, you're considering gauge supergravity. And so the isometry also appears in the Einstein-Hilbert term. And so together they give you a combined contribution of a Yang-Mills term downstairs. So we'll see how this actually manifests in terms of branes later. Right, so now you have this theory of this low energy effective action. So the first thing that we do is to construct the Wilson lines. And these Wilson lines, as we mentioned previously, are nothing but D3 branes that wrap some codimension 2 sphere in the S5. And so for our purpose, it'll be useful to also think of S5 as a Hopf vibration and circle vibration over CP2 base. And so this maximal 3 sphere would, in this language, be the same circle fibered over an S2 within the CP2 base. Now let us turn to the symmetry defects. And my claim is that this defect is in general a bound state of a D5 brane and a KK monopole. The D5 brane contributes precisely to the tau flux contribution, whereas the KK monopole contributes to the Einstein-Hilbert contribution in this low energy effective theory. So the way we construct this D5 brane is to wrap the D5 brane in some internal 2 cycle, such that this 2 cycle intersects non-trivially with the S2 in this S2 vector here. And once you do that, you can just do algebra and find that the hanging brane operator actually takes this form, which is the form that we want for symmetry generator. And now we can see how this A1 that's in the regularized defects appears in terms of brane degrees of freedom. This A1 is nothing but the Chan pattern degree of freedom on the D5 brane. And there's a similar story happening with the KK monopole. Even though there's no standard one-form gauge field on a KK monopole, but instead you have a pair of complex scalars on a KK monopole. And you actually when you try to write down when you read off the couplings, the topological couplings on a KK monopole, you'll find a coupling of the following form, which is A1 wedge pullback of G5, except that here A1 is actually a composite gauge field that is constructed out of these complex scalars. And so again, effectively, there's a one-form gauge field on a KK monopole that actually plays a role of having this A1, the flat connection in your regularized defects. And so right, so again, in the 2B picture, this will be literally a D5 brane or D5 brane plus KK monopole that's hanging here on a boundary. You pass a D3 brane across a D5. And it's well known that in 2B theory that you can have Hanane-Witten transition between a pair of D3 and D5. And what this does is that if you drag the D3 across this hanging D5, it drags out a phase. It's given by this Chan pattern along this gamma 1 here with some multiplicity factor n. And so what this tells you is that in string theory, what we observe is that you drag the D3 across D5, it gives you some F1 string that lies on this arc. And in field-theoretic terms, you can interpret this as the product of this charge QAB times theta AB, which labels the group element for your symmetry operator. And so this reproduces how charge measurement is done in holography. And so as long as we have this kind of observable, we can actually fully determine the irrep R of the Wilson line, or in other words, the D3 brane, by repeatedly measuring the charge here through different configurations of hang D5. And so this will help you map out the full matrix QAB here. Recall that QAB is not just a single number, but it's a block diagonal matrix. And so you can kind of, in simple terms, measure each block by smashing it with a different D5 with a slightly different internal geometry. And for completeness, we can also get spin representations, not in SO6, but in SU4, by setting QAB to be the half integral numbers. So you can determine all the Wilson lines in this fashion. Another slightly more non-trivial example, also in type 2B, is what's called a Klebanov-Witten theory, which is SUN times SUN gauge theory in 4D. The dual geometry in the bulk is ADS5 times T11. So here T11 again can be thought of as a Hopf vibration of S1 over a pair of two spheres. And this T11 structure is actually topologically equivalent to S2 times S3. So again, you see that there are some homological cycles. And so for this geometry, there's a richer symmetry structure involved here. So let's first look at the isometry sector. So there are two copies of SU2, which arises from the two copies of S2 in the base. And actually, for this purpose, it's actually more useful to think of the S2s as CP1s. There's an additional U1R symmetry, which is associated with the Hopf fiber S1 here. And since this T11 is topologically equivalent to S2 times S3, there's some additional baryonic symmetries. In particular, you can reduce the C4 RR4 form over the homological S3 and you get one form downstairs. So this gives you another symmetry, which is baryonic symmetry. So these are the symmetries that we'll be interested in reproducing in our construction. So let's focus on the SU2 factors. Now, again, similarly to the previous ADS5 times S5 example, you can construct three spheres. There's a circle vibration over the base CP1s. And so the two copies of SU2, their Wilson lines are respectively D3 branes wrapping some complex codimension 1 CPs times another S2 to saturate the legs and saturate the dimensions in your D3 brane. And you can actually write this down, sit down carefully and write this down, and you find that this kind of configuration again gives you Wilson lines for the SU2 factors. For the U1 factors, it's a slightly different game. For the R symmetry, you basically wrap a different cycle, which I don't want to talk about in detail here. And for the U1 baryonic symmetry, you basically wrap the D3 brane against the homological S3. So again, this is just to showcase that you can explicitly write down the Wilson lines by wrapping suitable manifolds in your geometry. And as for the symmetry defects, you can basically, again, find some bound states of D5 brane and KK monopoles. as long as they reciprocal manifolds in T11 that links non-trivially with your Wilson lines. So again, this is another slightly non-trivial example compared to ADS5 times S5 case, but the principle is basically the same. So let me also try to comment on how you can explicitly realize the fusion in the string theory terms. So in both of the previous examples, we have hanging D5 branes. And our claim is that you can smash a D5 brane such that it gives you a stack of D5. And what this does in detail is that once you bring two D5 branes close to each other, the pair of inner branes, which are opposite oriented, one is anti-D5, the other is a D5. Once you bring them close enough to each other, you have tachyonic modes developing between them. And so this will collapse the D5, anti-D5 and D5 into D4 brane in the middle. In particular, this is a not stable configuration. You want to blow it up back again into a pair of D5 and anti-D5. So this gives you another hanging D5. And you want to do it in a way that is consistent with the orientation. And so now you can view this hanging brane fusion as giving rise to a stack of two hanging branes. And there's one explicit way to dynamically realize how these hanging brane operators, which are supposed to replicate or mimic the regularized defect behavior in QFT, and how there's actually what I want to say is that there's a well-established string theory mechanism, a dynamical mechanism that reproduces this fusion in the QFT. Let me try with one last example, since I think my time is almost up, which is in M3, so it's different from the previous two big examples. So here I want to consider ADS4 times S7 in M3. Again, what I want to consider as an isometry here is SO8. It's dual to a 3D n equals 8 SCFT. So again, for the Wilson lines, I want to grab some brane on some codimension 2 sphere. So here, instead of D3 branes, the candidate to use would be M5 brane. And as for the symmetry generators, this would be, again, a bound state of an M5 brane and KK monopole. And I need the bound state of those to fully reproduce for me the Einstein-Hilbert contribution and the flux contribution and the low energy effective action. So one slight difference in this example compared to the previous one is that in the previous example, we make use of D5 branes, which has a one-form Chan pattern field. But for the M5 branes, you don't have a one-form word volume field. Instead, you have a chiral 2 form, B2. But the way to reconcile this is to make B2, to give B2 this ansatz such that it has a leg along the circle fiber in the Hopf vibration. And once you do this, you can find exactly the same result as before. In particular, there's a dual 2A description of this M5 brane as a D4 brane. And you can see this by actually seeing that if you reduce this M5 brane action against the S1 fiber, you'll get this kind of expression. This kind of expression is precisely the action that you obtain for a D4 brane with a standard Chan pattern field. And so there's a similar story for KK monopole. So since I'm out of time, I'll not go through the details. But the point is that, again, in holography, you can take this kind of M5 brane and N5 brane in M3. And in M3, the harmonic transition is between a pair of M5 brane, and what it does is that instead of having F1 branes, you get M2 branes localized on the arc. And again, there's a dual 2A description, which is that M2 brane is dual to F1 strings in 2A. So again, this is all fully consistent and compatible with each other. So we can see how in different kind of string theory setups, we can reproduce this kind of continuous charge measurement behavior for all, regardless of the Lie group that we're interested in. So there are a few generalizations we considered in this paper. Basically, we want to see that you want to view S5 and T1 as both members of this larger class of families, which are called the regular Sasaki-Einstein manifolds. And in all the cases, you can generalize this whole story to like wrapping things with D3 branes and also D5 KK bound states. And a similar story happens in M2 examples, where you consider Sasaki-Einstein 7 manifolds. And again, you can consider M5 KK bound states to reproduce this charge measurement behavior. So again, there's a lot of fun examples out there to work with. And our claim is that this can all be reproduced with a prescription of having these hanging branes. So let me wrap up the talk by saying that what we've done here is just the start of a very exciting exploration into how continuous symmetries play with each other in the context of holography, and how that actually reproduces the need for regularization in QFT. And one of our goals is to extend this to examples beyond Sasaki-Einstein manifolds, and to see whether this can hint at how to construct like rigorous derivations of SymTFT for continuous symmetries. Or if you're in a broader perspective, you can even ask the question of what is the fate of global symmetries in quantum gravity. And we do hope that our construction here will give us some hints on how to tackle these issues. So I'll just stop here for questions.
Thank you. I have a question. So have you considered ADS-3 examples, because your boundary is now 2D and gravity there is topological. So you shouldn't ideally have problems like collapsing the branes to a singular point, right? A singular line.
Yeah, that's what we would expect. We haven't actually looked at ADS-3 examples, but it'll be very interesting to see how whether the same kind of behavior happens, or if not, why. As you said, you have topological gravity there, and so
yeah, because you mentioned that dynamical gravity is one of the restrictions that prevent you from completely collapsing the structure. So if gravity is topological, then ideally you shouldn't have that, right?
That's a very good guess. And to be honest, I don't have a very clear answer of what to expect, since I haven't worked that out explicitly.
Okay.
But naively, you can still ask the question of whether you can regularize things, and whether you need to regularize things and whether you have to are different questions. So we have to be careful how to answer these.
Okay, thank you. Are there any other questions?
Yeah, I have a question. If there is some role that supersymmetry plays here, naively it looks like this configuration is a non-supersymmetry.
Yeah, that's a very good question. So the gauge groups that I've been talking about here are gauge groups that are responsible for internal symmetries of the dual gauge theory. So in particular, I have not talked about the space-time symmetries and supersymmetries. And so here, this is one of our goals to see how this can generalize, or whether this applies to space-time symmetries and supersymmetries in the field theory. That's work in progress, and I don't have a clear answer to give right now, but we believe that there should be something similar happening.
But the brane configurations that you have are non-supersymmetric
Sorry, for what?
In the examples that you have, these brane configurations, they're non-supersymmetric or the sort of non-supersymmetric.
Oh, you mean these hanging branes themselves, where there's
for example.
Yeah, these are not necessarily supersymmetric configurations.
Okay, thank you.
If there are no other questions, let's thank the speaker again.
Right. Is it possible to get the slides? Can you send the slides?
Yeah, sure. I'll be happy to send slides.
Okay. Well, thank the speaker again.
Yeah, thanks.
Thanks.